Okay, so thank you very much for watching this video. Today I will present towards a new era of non-stationary probabilistic tsunami hazard assessments. I'm working with Jennifer Haas, Philip Liu, Mircea Gregoriu, and Patricio Winkler from different institutions. So tsunami hazard assessment are very challenging, as many of you know, because we have, first of all, some difficulties trying to understand the physics of tsunami-genic sources. For example, try to understand them and try to model them. Then also we have some imperfect amount of data in order to try to do our tsunami simulations. For example, we lack of sufficient bathymetry information in some coastal areas. And also we have to deal with the fact that actually tsunamis have an uncertain occurrence. For example, we don't know when we will have the next tsunami in a given area. Okay, so because of this, we usually use a probabilistic tsunami hazard assessment or a probabilistic framework in order to address tsunami hazards in the long term. Okay, long term, I mean, for example, a project lifetime at the coast. Okay, so most of our work have focused on trying to improve the accuracy or try to improve this probabilistic tsunami hazard assessment. Okay, however, in the last few years, we have noticed that at the coast and in the ocean, there are some processes we are changing in time. And those changes are actually comparable to the typical project lifetime or exposure time of our projects. Therefore, we have some properties and some variables, some processes which are influencing our tsunami in the lifetime of a project. And therefore we have to consider them. Okay, so therefore the purpose of this talk is try to show you how we can formulate that stationarity in the environment in which tsunamis are propagating. Okay, to start before that, we need to describe what we are doing in terms of probabilistic tsunami hazard assessment. Commonly, we can adopt a binomial distribution model or a Poisson process in order to model the uncertain occurrence of tsunami events. So therefore, we have this P1, which is the first formula here I show you at the top, in which we have this kind of exponential distribution, which basically tell us what is the probability to have zero events in time. That lambda is basically the average recurrence of the hazard source. For example, we can think on lambda about the recurrence of earthquakes of a given magnitude. And T is the exposure time of our project or our project lifetime, this big T. Okay, if we include different type of earthquakes with different magnitudes or different seismogenic regions generating tsunamis, we can finally come up with a superposition of them because we are assuming are independent, and we come up with this formula for P2. But of course, not if you have two earthquakes of the same magnitude, you are not necessarily will have the same tsunami response because basically you have some uncertainty or some variability in the properties of the tsunami-genic source. For example, the slip distribution of an earthquake. Therefore, in order to address that problem and in order to deal with that variability, we come up with a thin version of a Poisson processes, which is the expression that you have here, the third expression. Okay, and in which we start to include different lambda i's, which is the tsunami-genic source, but then we have a penalty term here, which we call pi. And basically it's the probability to have, for example, a tsunami with a certain intensity exceeding HC, for example, the maximum surface elevation, given that you have earthquakes from the class or the ensemble EI, okay? And finally, if you want to really know what is the probability of having one or more tsunami events exceeding HC, finally, you need only to get the complement of this expression. And this is what we call the probabilistic tsunami hazard assessment based on a Poisson. Okay, so this is the expression that we have shown you in the previous slide. And now we have to think about, okay, What happens when tsunamis now are influenced by processes or properties which are changing in time? That is the big question. Okay, in order to adapt this formula, this traditional formula from the Poisson process, we have to go to the fundamentals of the Poisson model derivation. And we need to understand how we derive the homogeneous Poisson process or the stationary Poisson process, and go to that point in order to now modify it. So we have to arrive to a very small partition, delta t, okay? And that delta t is so small, in which, so the probability of having an event or zero events is 1. So you cannot have 2 or more events in that very small delta t. So finally, we arrive to this expression, which basically is the step in which we join, or in which we combine the binomial distribution with the Poisson process. This is the point in which both met, okay? But that is not so important. Well, it's important for the people dealing with binomial distribution, because basically here I'm showing you that we can use both models in order to apply this non-stationary perspective. Okay, but the important thing here is that if you have this delta t, the next delta t will be completely independent of what is going on here. Therefore, in order to now consider all the delta t's from 0 to the exposure time t, we just need to do a sequence of independent Bernoulli trials in which you have probability of having 0 events or having 1 event. And finally, if you do the product, which basically will consider all the different delta t's, you can rearrange the formula of this exponential, and finally you can come up with this expression in which now you have an integral. And in that integral, now you are considering that this pi, or even lambda I, which is related with the earthquake, can change in time. And this is very cool. With this expression, now I can show you that you can deal with any process influencing tsunamis as long as you can solve for this value of pi for different times. And that S is basically a sea state, okay? It can be the sea level, for example, and that will change because of sea level rise. It can be, for example, changes in the bathymetry, because, for example, you are doing a big reclamation and you have a big port you will build in front of a city, for example, etc. You can combine, you can consider different things that are changing the conditions and the tsunami response in the future. Okay, so finally, using that integral, we can come up with this expression, which is what we call the non-stationary probabilistic tsunami hazard assessment. And if you see with the, if you compare with the expression at the top, which is the traditional probabilistic tsunami hazard assessment, you can see that actually the difference is this integral, which now considers different values of pi in time, while the other one is considering a constant pi. Okay, that is the main difference of this non-stationary probabilistic tsunami hazard assessment. Very cool that pi can consider different states or different properties which are changing in time. And as far as our study is concerned, we have considered that lambda I is constant, so therefore we are removing it from inside from the integral. But if someone is interested also, they can use the lambda I and they can change lambda I, for example, because they have different earthquake recurrence in time. Okay. Okay, so in this example or the analysis I will show you, we will deal with sea level rise. So S will basically be the sea level. Okay, that is the sea state which is changing in time. And a big question before to do an example is how we can solve for that integral. Actually, when you are doing a traditional probabilistic tsunami hazard assessment, the computation of PI take a lot of time. Using my laptop, typically for the South China Sea, which is the example we will see later, typically it takes me like 1 month in order to compute all the PIs for the different earthquake ensembles I. Okay, so therefore we need to find a numerical way or a numerical approximation in order to solve for that integral. Okay, and that is what we design in this study. And this strategy that we will use, we call it the surrogate model. So basically how this works. Okay, so In this plot here, I will show you this plot in order to illustrate the technique. We have a plot of the distribution PI, okay, for different values of HC or different values of critical maximum surface elevation. So what we do here is that we will run now 3 or any number of traditional probabilistic tsunami hazard assessment. But for each of these probabilistic tsunami hazard assessment, we will consider a certain constant level offset from the zero. In the red line, for example, we have a 0, 0. So we are considering that the mean sea level is the same as today. In the blue one, now we consider a sea level which is a little bit higher than that 0 value. For example, the sea level that you will have in 50 years more. And then you have the CN curve, which consider a larger offset. For example, the sea level you expect to have in 100 years. Okay, so what we do now is that we build these different traditional probabilistic tsunami hazard assessment with different offset. And in order to consider the probabilistic tsunami hazard assessment for any time, or this PI for any time, we start to do a linear interpolation along the H direction. Okay, so by doing this technique, we can now obtain a surrogate model to obtain different values, different curves PI for different times or different sea levels. Okay, so finally, we have this numerical technique in order to solve for any PI in any time, and we can combine them with a trapezoidal quadrature, for example, in order to solve for this integral inside the non-stationary probabilistic tsunami hazard assessment. So nailed it. Wonderful. We have the formulation, we have the numerical implementation. Now we can test it in a non-stationary probabilistic tsunami hazard assessment in any region. Okay, let's see that example. So of course, as an example, I use some work I have from previous papers. In specific, I'm using this probabilistic tsunami hazard assessment in South China Sea. Okay, for this evaluation, for this assessment, we already have the values of lambda I, and indeed we have 3 different types of lambda I. Okay, for different recurrence of different earthquakes with different magnitudes. We also have different models or samples for the earthquakes, which basically is the uncertain variable. In these earthquakes or synthetic earthquakes, we are considering uncertain slip distribution and locations. And here you can see 2 samples of magnitude 9 earthquakes in the Manila Trench. And we use those samples in order to calculate or in order to determine the distributions PI, which in this case is a single PI with a constant value of 0, the sea level of today. Okay, so we use 11 different earthquake ensembles. That means that we have different earthquake magnitudes with different locations. Okay, and we use the Comcock tsunami model in order to do the tsunami simulation. And we also use the SRAM uncertainty propagation instead of a Monte Carlo, which optimizes the time. So it minimizes the time of computation. So here you have the typical hazard curves for 6 locations in Kaohsiung and Hong Kong, okay? And you can see here the maximum tsunami elevation and their corresponding probability of exceeding that value given an exposure time of 100 years. Okay, so now in the non-stationary probabilistic tsunami hazard assessment, we have the problem that the sea level is changing in time, okay? When using the traditional probabilistic tsunami hazard assessment, we will see that this lambda n, which is basically pi times lambda I, is constant in time. Okay. Now, for the non-stationary probabilistic tsunami hazard assessment, we have that this term is changing. It's changing not because of lambda I, because we are assuming that that is constant, but it's changing because the pi, which here we call it as a big P, is the same as the pi from the previous slide, is changing in time. So let's see what is the effect. This curve is lambda n, okay, which is completely invariant when you are using the traditional probabilistic tsunami hazard assessment. Now, when you are using the non-stationary probabilistic tsunami hazard assessment, this curve start to change. Why? Because tsunamis are riding over higher sea level. It's completely expected that now the recurrences of a certain tsunami exceeding HC start to increase because the sea level is helping them to reach higher land. Okay, let's see again this evolution. Okay, great. So it's doing what we are expecting that tsunami is supposed to do when we are rising the sea level, right? Okay, now in this plot, I will show you the non-stationary probabilistic tsunami hazard assessment in 6 locations. Again, 3 in Kaohsiung, 3 in Hong Kong. In the segmented line now, the black segmented line, we have the curves of the traditional probabilistic tsunami hazard assessment. In the cyan, red, blue, black, and the gray area, we are showing different projections of the sea level rise in South China Sea. Okay, those are not done by me. Basically, we obtained it from a paper from 2016 projecting the sea level rise in that region. And basically, the different curves are different scenarios or different projection of the sea level rise. And the gray line is basically the uncertainty that we may have with one of the worst or conservative scenarios, which is the RCP 8.5. Okay, and what we can see is that the sea level rise actually has a very important effect on the probabilistic tsunami hazard assessment in this area, not only in Hong Kong, but also in Kaohsiung. And another plot that I want to show you here is the 6 lower panels, which show you actually what is the relative difference compared with a traditional probabilistic tsunami hazard assessment. And you can see that actually the probabilities are increasing hugely because of this effect of the sea level rise. So the sea level rise is important and is modifying our probabilistic hazard curves. Okay, in terms of inundation maps, here I'm also showing you what is the probability to inundate a certain region in a given exposure time of 50 years for the left columns and for 100 years in the right columns, okay? So in the top panels, I'm showing you the traditional probabilistic tsunami hazard assessment, and in the lower panel, I can show you what happens when you are including sea level rise in this non-stationary framework. And you can see that actually in 50 years, more or less, the probabilities doesn't change too much. But when you are going to the 100 years of exposure time, the effects are very important. Okay, but comparing different different evaluation points in Kaohsiung and Hong Kong, indeed what we can see is that actually the effect change a lot, is variable. The impact is not always high in all the regions. Only in some places you will see that this impact is important. And where is that? Where is that happening? That is happening in the places where the tsunami with a medium or middle probabilities are comparable to the sea level rise that we are analyzing. For example, if you are analyzing a very huge tsunami, for example, those that happen in Chile or in Japan, you will see that actually the sea level rise won't affect your probabilistic curves or your inundation maps so drastically as these cases in Japan, in Hong Kong, sorry. So this is a very important thing because now we have to think, okay, how we can measure that influence of sea level rise in probabilistic tsunami hazard assessment all around the world. And not only sea level rise, we have to see, for example, what happened with other changes in time. For example, what happened when you are doing a big master plan for a port and you are doing a reclamation of land, how you will affect the tsunami hazard of a given city next to the port, for example. So it's important that we can use this formulation for not only sea level rise, but for other type of changes in time. Okay, finally, just future work. We are now working with tides. We want to understand what is really going on with tides, if tides or sea level rise are more important. And we already finished that work. We hope to publish it very soon. And what we can see is that at least in Kaohsiung and Hong Kong, the effect of tides is small as compared to the effect of the tide is small as compared to the sea level rise. Okay, and here in this plot I can show you the probabilistic tsunami hazard assessment in the top left without anything. Then you have in the left top the PTHA with sea level rise. Then down here in the left, at the left, you can see PTHA with tides. And finally, the combination of everything. And you can see that actually the tides is not so important, or the role of the tides is not as important as the sea level rise. So finally, just a conclusion, I want to show you this, what I understand as the timeline of the evolution of tsunami studies. Of course, we started with the 50 with analytical solution, then we started to work with numerical models. After 2006, after the great paper of Eric Geis and Poisson, we started to work with a probabilistic tsunami hazard assessment, which is very cool. And we say that after 2014, 2015, we started to think about how can we have some temporal changes in the conditions so our tsunamis are changing. And this is what we call the non-stationary probabilistic tsunami hazard assessment. So that's all, and thank you very much. And if you have questions, of course, I will be happy to answer them during the session. Thank you.